The next topic we want to consider is uncertainty in measurement. So primarily we're going to talk about significant figures, rounding rules, how to appropriately report a value when we've done addition and subtraction versus how we would do it if we've done multiplication or division. So when we're talking about significant figures, it's referring to digits that we're measuring and calculations we're doing with measured values. So when we're rounding off our numbers to report an answer, we want to pay attention to significant figures so we don't overstate the accuracy of our answers. So we want to round appropriately so we're properly describing the value that we're actually looking at. So we'll start by defining how we can identify the significant figures in a particular value. So here I'll just tell you the four main rules, and then on the next slide we'll look at some examples. So first, all non-zero digits in my number are significant. Obviously talking a lot about zero here. Zeros that are between two significant figures are significant. Zeros at the beginning of a number are never significant. So the beginning of a number would be to tell us where we start counting from. It's just a placeholder, so that's not going to count. And then lastly, zeros at the end of a number, so on the right side of the number, they are significant as long as the number has a decimal point. So that's a really important point to make there. So as long as the number has a decimal point anywhere in the number. Okay, so I think it'll make the most sense to look at examples of these cases. Any digit that is not zero is significant, so 1.234 kilograms, that would be four significant figures. Zeros between non-zero digits are significant, so 606, all three of those count. Zeros to the left of the first non-zero digit are not significant. So there's only one significant figure in 0.08. Those are just placeholders, right? They're telling us where to start counting from. So that would be the only significant figure. All zeros to the right of the decimal are significant. So just to make that clear, right, 2.0, both of these are significant. And then just to be a little bit more direct with that, zeros at the end of a number are significant if the number contains a decimal. So the first example is following the same rule. So 4 to 0, all of those would count. The previous rule, they count as significant to the right as long as there's something that precedes it. So in 0.00420, only the 420 counts. The other three are placeholders. Then the last example, this is pretty different from what we usually see, but notice that there's a decimal point right after the 0 and the 1's place, and that's what I need to do in order to indicate that the 0 in the 1's place counts as significant. So just to be clear, right, 2040 no dot, that's three significant figures, but 2040 dot, that's four significant figures. And then that's different from 2040.0 because that would be five significant figures. Okay, so those are kind of the fundamental rules to think about with all of that. So hopefully that's making okay sense to start out with. Okay, so let's move on from there. And then here are just some more examples to look at. Okay, so now If you're in the slides, I think these pop up, but we just kind of have it all in one place here. So I'll kind of highlight where the significant figures are in each case. Okay, 24 milliliters, pretty clear, right? Those are our two significant figures. 3001, all four of those count. 0.0320, it's these, right? 320. Those are our three significant figures. Okay, now we have a number in scientific notation, 6.4 times 10 to the fourth. So that's really 64,000, right? 6.4 times 10 to the fourth would be scooting my decimal 4 places to the right. So scoot to the right of the 4, then add 3 zeros. So that's what we get there. That doesn't mean the decimal is at the end of the number, right? So in scientific notation, we just really base the number of significant figures on what they give us prior to the exponent. So this is just going to be two significant figures, the 6 and the 4. 560, no dot, the 5 and the 6 count, so those are my two significant figures. 560 dot, all three of them count. And then just to compare to what we did before, right? 560.0, that would be 4 significant figures. All right. So now I want to talk about how we're going to apply these rules depending on whether we're doing addition and or subtraction. And then after that, we'll talk about our rounding rules a little bit. Okay, so here again, I'm telling you the rules, and then we'll sort it out more clearly after that with examples. When addition or subtraction is performed, answers are rounded to the least significant decimal place. So whichever number has fewer significant figures after the decimal place, that's going to dictate how many digits I include. For multiplication and division, it's going to be different. It's going to be based on the fewest total number of significant figures. So that should make sense, right? Addition and subtraction, I line things up with the decimal, so the location of the decimal should be important to deciding how many significant figures I include. But in multiplication and division, normally I multiply and then figure out where the decimal goes afterwards. So its initial location isn't important, so it shouldn't affect the location of, or the total number of significant figures. Okay, so let's talk about rounding off, and I think the fundamentals of this are things you're surely confident with, but there are rules related to the number 5 that we're going to see that may be a little bit different from the way you initially learned about rounding off. Okay, so when we're rounding off, we're going to go one digit to the right of where I want to cut off the number. So when we talk about the cutoff number, that's based on the rules telling us what's the last digit that we want to keep based on the rules about addition and subtraction or multiplication and division. And then we go one digit to the right of that. If the value after the cutoff number is larger than 5, then you increase the cutoff number by 1. If the value is smaller than 5, then the cutoff number stays the same. So that should be old news, right? And notice we didn't say anything about what if it is 5. That's what we're going to address next. So we're going to talk about something called the odd-even rule, and this is probably the part of rounding that may not be familiar to you. Okay, so again, we're still talking about the digit to the right of the cutoff number. So if the value to the right of the cutoff number is 5 and no other digits follow, that's when we use the odd-even rule. So when the cutoff number is odd, the cutoff number is rounded up 1, and when the cutoff number is even, then the cutoff number is going to stay the same. So look, this is very different, right? It's talking about a specific case where the cutoff number is followed by a 5 and nothing else. And in that case, whether the cutoff number is odd or even is going to dictate what we do. And 0 would be even for these purposes. So basically what that ends up doing is it tells me half the time I'm going to round up, half the time I'm going to do nothing. So we'll look at examples of this in the next few slides, but let me show you one here just to kind of give you an idea. So let's say, for example, that I have 33.2, oops, no, that'll be my example for the next one. Let's say I have 33.35, and for whatever reason, based on the particular problem, I identify this 3 as the cutoff number. So this is a case that would qualify for the odd-even rule because the value to the right of the cutoff number is 5 and no other digits follow. So 33.35 is exactly halfway between 33.3 and 33.4. So there's no obvious way for me to decide what to do about rounding, so that's when the odd-even rule applies. So like I said, the concept is half the time I round up, half the time I do nothing. And we need to agree about which half we do one thing, which half we do the other, so everyone's being consistent. And the odd-even rule says when it's odd, I round up, and when it's even, I don't do anything. So 33.35 would round to 33.4 based on the odd-even rule. But if I had 33.45 and I was told that 4 is the cutoff number, now again the odd-even rule applies, but now since the cutoff number is even, I don't do anything. So it'll stay as 33.4. So basically, like I said again, it's half the time I round up, half the time I don't do anything. So over a large collection of data, that should work out. Okay, so I think I have another collection of round-offs that I've done, and that'll give us a chance to look at the odd-even rule along with these other rules, and we'll talk about one other idea as well. Okay, so for the odd-even rule, let's look at these two. Round 16.35 to 3 significant figures. 3 is my cutoff number and it's odd, so this would round to 16.4. And then the second example, round 16.65 to 3 significant figures. 6 is even, so I don't do anything, so it would round to 16.6. Okay, so then here's a series of numbers to look at for rounding. All of them are rounding to 3 total digits. So we'll identify the cutoff number in each case and kind of walk through our rounding. So 68.34, that makes 3 the cutoff number. It's just followed by a 4, so less than 5, so it stays as 68.3. 3528. 2 is the cutoff number, but it's followed by 8, which is bigger than 5, so we round up to 3530. So I still need that 0 there, right? If I just called it 353, then it wouldn't be 3,530, it would just be 353. So make sure you're keeping the same numerical value when you're doing this. If something rounds up like that, it still needs to be there as a 0, so that's what happens in this case. Okay, this third one, 9 is my cutoff number, and it's followed by 5, 2. Generally, I don't look more than one digit past the cutoff number. But if the digit just past the cutoff number is 5, then I need to look past it. If there's nothing there, like in the next two, that's when the odd-even rule applies. But if I've still got values after that 5, that's going to affect the rounding, right? 0.3295 is halfway between 0.329 and 0.330. 0.32952 is closer to 0.330. So in this case, I need to round up to 0.330. So you should see from that the odd-even rule applies in only very specific cases. Remember, the language said if the cutoff number is followed by a 5 and nothing else, that's when odd-even rule applies. But if there's something after the 5, then technically that makes it closer to the next number up, so we're going to round up. Okay, a little more odd-even with these last two cases. 6465, where 6 is the cutoff number. Since the cutoff number is even, we're going to stay put, so that'll round to 6,460. And then in the last one here, 563.5, 3 is the cutoff number. It's followed by 5 and nothing else, so both of these are cases of the odd-even rule. This one is not the odd-even rule because there's numbers after that 5. But so following the odd-even rule for the last one, since 3 is odd, we round up to 564. Okay, so that should kind of cover the basics for rounding. So now we'll apply it to addition, subtraction, multiplication, division. Okay, so addition, subtraction, here it's phrased a little bit differently. The answer cannot have more digits to the right of the decimal point than any of the original numbers. So if I add in my calculator 89.332 and 1.1, I get 90.432. Since 1.1 only has one digit after the decimal, then I need to round to only one digit after the decimal. So that makes 4 my cutoff number. So if 4 is my cutoff number, then I look to 3. 3 is smaller than 5, so it just rounds to 90.4. Okay, subtraction. So now I've got 3.70 minus 2.9133. 3.70 only has 2 significant figures after the decimal, so I can only have 2 significant figures after the decimal. So now that makes 8 my cutoff number. Then I look to the 6 that's after it. 6 is bigger than 5, so we round up to 0.79. All right, then how about for multiplication and division? Oh, I lied. We're going to do these examples first, then multiplication and division. Okay, so same like before. If you want to pause and do these yourself, that's fine. If you just want me to keep going, that's fine as well. Okay, let's see what I get. 34.222 plus 16.51. The calculator gives me 50.732. Well, of the two given values, 16.51 only has 2 significant figures after the decimal, so that means I can only have 2 significant figures after the decimal. So if 3 is now my cutoff number, 2 is what follows it, so it's just going to round to 50.73, right? I don't go up, I just leave it as is. Okay, the next one, 13.464 plus 9.31. The calculator gives me 22.774. Of the two values I've got, 9.31 only has 2 digits after the decimal, whereas 13.464 has 3. So now I'm limited by the 9.31. That makes the second 7 my cutoff number. it's just followed by a 4, smaller than 5. So when I round off here, it's just going to be 22.77. Okay, hopefully so far so good with that. Okay, now we're going to talk about what happens with multiplication division, and then do a couple examples of that as well. So remember, with multiplication and division, we're worried about the smallest total number of significant figures. So in the first example, we have 4.51 with 3 significant figures multiplied by 3.6666, which has 5 significant figures. So now we're basing it on the total. And remember, I kind of rationalized that by saying the decimal point location is not relevant to the operations of multiplication and division. When we do it by hand, we place the decimal after the fact. Okay, so what that means here is now I can only have my answer to 3 significant figures, so 16.5. So if 5 is my cutoff, then I look to the 3, which is smaller than 5. So we round to 16.5. That arrow is not pointing at anything in particular. I think it may have just moved, but the 5 is the cutoff number. Okay, in the next example, I have a value with 2 significant figures divided by a value with 5 significant figures. So, oops, I'm going to keep doing that. So my answer can only have 2 significant figures. That gets me to the 0 after the 6, right? This 0 here is going to become my cutoff number. It's followed by a 6, which is bigger than 5. So in this case, I round up to 0.061. Okay, same thing here. Here are a couple examples that I'll work out. You're welcome to pause the video and do them yourself first, or again, just keep going. I promise I'll stop saying that after a little while. Okay, first one, 3.422 times 16.3. My calculator gives me 55.7786. 16.3 has 3 significant figures. 3.422 has 4 total significant figures. Remember, we're worried about the total since it's multiplication and division. So in this case, that would make this first 7 my cutoff number. It's followed by a 7, so that means I round up. So it'll be 55.8. Okay, the next one, let's see what the calculator gives me first. 9.15142 times 32.41. Lots of digits here. 296.597522. So we really wouldn't want someone reporting our answer like that, right? So we'll follow our rules here. 9.15142, that's 6 total significant figures compared to 32.41, which is 4 total significant figures. So with 4 total, that would make this 5 my cutoff number, and it's followed by 9, which is bigger than 5. So this would round up to 296.6. Okay, so that's really all of the rounding stuff that I wanted to talk about. One more idea to look at, and then one more concept, some terminology stuff, and then that'll do it for this video. Okay, so I want to talk about the idea of exact numbers. And so one of the things we're going to see a lot of are numbers from definitions. And for example, like 1 inch equals 2.54 centimeters. Or if I have a constant that I'm using that has a particular value, those are numbers from definitions. And when we think about those, we say that they have an infinite number of significant figures. So with that idea in mind, it basically means it won't affect a value. So if I'm using a conversion factor that looks like it just has one significant figure, like this one, 1 inch equals 2.54 centimeters, that's the exact conversion between those two units, so it's infinitely accurate. So what you'll see, and we'll talk about this probably in the next video, is when I'm doing calculations where I'm using a value from a definition, then the original number of significant figures is typically what will dictate what I actually report. Kind of a silly example of this is when we take an average, right? If I'm averaging these three values and the process of taking an average would be add them together and then divide by 3, then when I do that, I'm going to want to follow significant figure rules to get the correct value. But what I don't want to do is say 3 has one significant figure, so I'm going to round off to 7. That would defeat the purpose of it. So this is one example of an exact number. We'll see taking averages in some of the lab data probably, but more often in lecture we're going to be seeing values from definitions like unit conversion factors. So make sure you're considering that as infinitely accurate for the purpose of unit conversion. Okay, one last thing here. Kind of some standard vocabulary that we want to be familiar with when we're talking about collections of data is accuracy versus precision. So dartboard is kind of our classic analogy for accuracy versus precision. So let's talk about these two definitions and then walk through our dartboard examples. Accuracy refers to the proximity of a measurement, one single measurement, to the true value. So proximity of a single measurement to the true value. So accuracy would be I throw one dart and we see how close that one dart was to the bullseye. So I can take one measurement and describe that measurement as either as accurate or inaccurate. So that's accuracy. On the other side, I have precision. And precision is talking about the proximity of several measurements to each other. So I can't be precise with one measurement, right? I need several measurements in order to be precise. And essentially, precise means that all of my measurements are relatively close together, and being imprecise would mean that they are not particularly close together. Doesn't say anything about its proximity to the true value, but it just says that they're close together. Okay, so let's look at our dartboard over here. So the first example is showing a case of good accuracy and good precision. So each dart is near the bullseye, but the collection of darts are also near each other. So each individual throw is accurate because it hit the bullseye. The collection of data is precise because they're all together. Remember, precision doesn't tell me about proximity to the true value, just proximity to each other. The middle case is poor accuracy but good precision, right? All three darts are close together, but none of them are at the bullseye. So not good accuracy, but good precision because they're all close together. And then the last one is kind of the worst case, poor accuracy, poor precision. No one throw is close to the bullseye, and the individual throws are not near each other. In terms of a scientific experiment, of course, the first case, good accuracy, good precision, that would be ideal. That would be a great experiment. The second case is okay, though, right? It means my experimental method is good because I'm getting consistent results. Just maybe I'm not considering a particular parameter, and that's why I'm missing the actual true value, but at least the experimental conditions are repeatable. The bottom case is definitely the worst case, right? Each trial is not close to the true value, and they're not close to each other. So not only is my experiment not getting me close to the true value, it's not repeatable because I'm getting drastically different data each time. So that would be the least desirable case. But that's also a good reminder, right? I can't just look at an experiment and look at the average value and say that it was a good experiment. I need to see the raw data to understand whether they missed all over the place and just the average happened to work out, or if the data was relatively precise to start with. Okay, so let me go ahead and stop this video here. I think we'll probably have one more video to wrap up the last slides in this section, but yeah, I'll go ahead and stop here.